now? Okay. Okay, let's get started then. I noticed looking at my very first slide that there's already a mistake in my talk, which is I'm using a title from another talk on this slide. I think I copy and pasted the file from one talk to another one, and so I'm going to be talking about not output, not sensitive, well-separated pair decompositions, not dynamic. Okay, point set. So ignore three of the words, any three words on this slide you like, and that will describe my talk. But the talk today is going to be just a generic talk about well-separated pair decompositions and some of their applications. Some of this may be material that's familiar to you. I know at least one of you who's doing research in the area of well-separated pair decompositions. But I want to talk about this because my next couple of lectures, well-separated pair decompositions are going to play an important role in those constructions, the algorithms. And so I want to make sure that everybody kind of understands the concepts here. So, okay, so let me begin with the definitions here. In fact, maybe before I give the definitions, I should mention something by way of motivation for those of you who've not seen this concept. So the well-separated pair decomposition was an idea that is actually not invented in the realm of computational geometry. Well, let's say the motivation did not originally come from computational geometry and theoretical computer science. It actually arose out of computational physics. And for those of you who've studied something called the fast multipole method, the FMM, this is a technique which is used in physics to essentially to process interactions between large systems involving pairs of objects. The idea being that if you, let's say if I have a large number of particles in a system, these particles are interacting, I have n squared. So if I have n particles in my system, there are n squared pairs of particles that could interact with each other. And the idea behind the fast multipole method was a technique to reduce from n squared down to just n things that have to be considered. And this idea was picked up in the area of computational geometry in the form of what's called the well-separated pair decomposition. So let me begin with the definition here. So the well-separated pair decomposition is based upon a parameter called S, which is the separation factor. Okay, we're going to assume that S is greater than or equal to 1. We say that 2 points A and B are S well-separated under the following circumstance. So if they can be A and B can be enclosed in balls of radius r, and this applies, by the way, in any dimension. So these are just the Euclidean balls of radius r, such that the separation distance between them is at least s times r. Okay? And using the idea of a well-separated pair, I can now define a decomposition. Okay, so what is a well-separated pair decomposition? Well, given a point set P, the S well-separated pair decomposition is a set of pairs AI, BI. So going back before, right, this will be an AI, this will be a BI. But I want to imagine now that if I give you an entire set of points, I want to break all the pairs up into groups of separated pairs. Okay? So it'll be a set of pairs AI, BI for some number k, let's say. We'll talk about how big the value of k is later on. So each pair AI and BI should be S well-separated. Okay, and it should be the case that for any pair of points P and Q in my original point set, okay, there should be some well-separated pair that represents that. So for example, this point P and this point Q, there is this well-separated pair here, right, this guy and this guy, and these guys essentially represent that pair. So this diagram here is, I'm not sure if you can kind of read this, but the idea is, these 2 points individually are well separated. By the way, individual points are always well separated. This represents a well separated pair between these two and these two. This line here, well separated pair between this set and this one point here. This line here, right, a well separated pair between this guy and this guy. And if you take any edge of this graph, you will observe that that edge will be represented by some well separated pair over here, right? There'll be some pairing involving one of these, right, one of these blobs here with this guy. And in general, of course, this is a very small example. In general, these things will exist at various scales. So for example, if I had, let's say, a very, very large point set that covered the entire wall, it might be there's a large, well-separated pair that encloses all of these guys that would be joined with maybe some, with some other set far away. So you'll notice that in a well-separated pair decomposition, these sets will occur at various scales of resolution. Okay. So the concept of the well-separated pair decomposition was introduced by Callahan and Casaraju in 1995. And the important result here is that they're given any n-element point set in d-dimensional space, and given any value s, the number of pairs you need in a well-separated pair decomposition interestingly grows linearly in n, right? The normal number of pairs that you have is going to be n choose 2. That's going to be quadratic in n. But the idea here is if I'm just looking at well-separated pairs, I can always find some number of pairs in which there's a linear dependence on n. And then there's a dependence, of course, on s. Because as the value s gets bigger and bigger, right, the pairs have to be more and more well-separated. I'm going to be needing more pairs to represent these things. And I'm going to give a proof of this fact later on, but I just want to state it for now. Okay, so this, in other words, you can think of this as a way of providing a concise encoding of the n-squared pairs of your set using, well, depending on the value of s, right? Again, I want to imagine perhaps that n is a very large number, perhaps on the order of, hundreds of millions of points that I have in my system to deal with. And s, right, is going to depend on the accuracy with which I want to do my computations. So if I think of usually a computation where I want an epsilon error, many times s is going to be of the form 1 divided by epsilon, or within a constant factor of 1 divided by epsilon, where epsilon represents my error. So the error term grows essentially as s raised to the power of the dimension. Like I said, I'm going to give an explanation as to why this is the case. And it can be constructed in time that is essentially n log n plus a value that is sensitive with the size of the output. Okay. So let me talk about how to build these things. And by the way, as in yesterday, if you have any questions, please feel free to interrupt me. So the construction for well-separated pairs is based upon a variant, let's say. An efficient construction is based upon the variant of the notion of a quadtree. So let me just remind you, a quadtree is a hierarchical decomposition of space into cubes, I guess. So I assume by beginning that all the points initially have been scaled down to a unit cube, right, from 0 to 1 in each of the dimensions. And then this is my initial basis cube. If I divide a cube into 2 to the d boxes, let's say, of half the dimension, then these are all quadtree boxes. And if I continue to do so as well, I get quadtree boxes. And then a quadtree in general will be given a set of points. I would like to just define a tree which is formed by decomposing things until every one of these boxes contains at most one point. The normal way in which these things are encoded, right, is I can think of this 2 to the d array tree as represented, let's say, southwest, northwest, southeast, northeast. So these would be the children of the tree. And so in this case, I can encode this tree in this, in this particular manner. Quad tree, because of course there are 4 children. 3 dimensions, you have an octree. In higher dimensions, I don't know what the name is for, a 7-dimensional tree with 2 to the 7 children. So we just call them quad trees in all dimensions, I guess, for ease. Okay, let me make a couple of comments, though, about the actual construction. So this quadtree, which is sometimes called a PR quadtree, which stands for a point region quadtree. Unfortunately, if you use this idea directly, it will not lead to an efficient construction. So there are a couple of modifications that are necessary. The original paper by Callahan and Casaraju introduced something called a fair split tree. And I'm going to describe a different style of a data structure, mostly because I'm going to use this data structure in later talks. This tree is going to be called either a BD tree or a BBD tree. So let me describe the issues here. So the first issue is this, that if I have a pair of points that are very close together, right, notice that the space needed by the quadtree cannot be bounded as a function of just n alone, right, because it'll depend upon the actual proximity of these points. If I have, a universe that is many light years apart and I place a pair of points that are angstroms apart, then I have to do many, many levels of decomposition before I can split these guys. Okay, so there's a nice, simple way of fixing this idea. And this is done by, we introduce a different internal node in our tree. So up until now, all the internal nodes were simply these, what we call a splitting node. It would just split a box into, let's say, 4 or 2 to the d boxes. But I'm going to introduce a new internal node called a shrinking node. And the way the shrinking node works is it stores internally a representation of this quad tree box that encloses these points. Okay? One of the children will be what's called the inner child. So the inner child will contain this stuff here. Okay? And the outer child is this thing that I call a donut cell. So what is a donut cell? Well, it's a cell that has essentially empty space around the outside, and there's a hole in the middle. Okay? So this cell is sort of representing this region of space. This hole in the middle, representing this stuff, is actually part of the inner child here. Okay? And then the thing to observe is that because the inner child is chosen to be the smallest enclosing quad tree box, then I know that at the very next split, I will be able to make progress in the sense that I will have, at least 2 of the children here will be non-empty. Okay, do I have anything else to say about this? Yes. So the donut cell is this, let's say the cell associated with the donut is not just a cube, but in fact it's the set theoretic difference of 2 cubes, the outer cube and the inner cube. Okay? And the important thing about this data structure, so by the way, this goes under the name of BD tree. So I guess I didn't write it out, but BD stands for box decomposition. So a box decomposition has, because of this property here, with every pair of splits, let's say with every 2 levels of splits, you always get a non-trivial decomposition, right? So you're always going to have, amongst the children that you have here, 2 of them are going to be non-empty. So for this reason, the space is going to be linear in n. The amount of time it takes to build this tree is going to be n log n. It takes a little bit of cleverness to do that. But one thing I'm going to observe is you might say, well, wait a minute. How about the height of this tree? Is the height of the tree going to be logarithmic in n? And you can see that in general it's not going to be logarithmic in n. And I'll deal with this issue next. So the problem here is that the height in general could exceed log n. For example, if you have this, let's say, a geometric series of points going up, okay, and you'll wind up with this degenerate structure here. So there's a nice way of fixing that as well. And this is done by an operation which is also related to a shrink, but it's what we call a centroid shrink, centroidal shrink. So a centroidal shrink does the following. What we're going to do is we're going to perform the same kind of an operation. So I'm going to have a cell here that's going to be basically, it's going to store within it a rectangle, that rectangle in the upper corner. Okay, there will be 2 children. The inner child will be for all the points inside of that. The outer child will be for the donut. Okay, now the donut is a little different because before, I guess, right, in the case of the donut, there was nothing on the outside. But in this case, there will be points on both the inside and the outside. So the outer child will store the cell that consists of this outer region minus that inner region. And the idea here is that I can do this in such a way that I would like to balance the number of points between the inner and the outer. Okay? And the claim is that this can always be done so that a constant fraction of points are on the inside and a constant fraction are on the outside. Yes, if you want to think about exactly what that fraction is, you can do so. It in general depends upon the dimension. If you're doing this using a binary split, you can generally guarantee that there's like a 1/3, 2/3 balance between these things. But because we're dealing with quad trees, the split is not going to be generally that balanced. But in general, there's going to be a constant fraction of points that can be guaranteed to lie in each one of these things. Okay? So here's the idea. For this point set, I can do a centroidal split at the very beginning. The inner cell will store those guys. Now those guys happen to be, in this particular instance, I could do a centroidal split, or I could just continue with the standard quad tree split. So in this case, if I just did the regular quad tree decomposition, right, I would get, well, this point here corresponds to this point up here, and then these 2 guys down here are going to correspond to those 2 guys up there. Okay? And then on the outer child, again, the structure is basically the same. Right? So I can do one standard quad tree split to separate this point from the other 2, and then a second split will separate these 2 guys. Notice that one of the cells in here, right, this little hole that I had in the donut has to be represented somewhere. So these black points represent the points here. This guy is going to be a donut cell. So this corresponds to, I guess, which? This cell up here, right, has what? It's broken into 4 children. One of them has a point. That's this one here. and the other one has this kind of hole that's been eaten out of it. Actually, in this guy's case, the entire box is the hole. So this is a very disappointing type of a donut. You can have donuts where the hole is so big that it actually is the entire shape itself. And yes, I would not want to go to a donut place and have somebody give me such a donut where they say, hey, it's a donut. It's just that, it's just that the hole is grown so large. This we call a BBD tree. So in this case, it's a balanced box decomposition tree. The balance refers to the fact that you now have height that is going to be logarithmic because of these centroidal splits. So you have space n, height log n, and the build time is n log n. And I'll mention, by the way, that there are a lot of different data structures that have roughly these same properties. The BBD tree was the one that I guess I developed with Sunil Arya in some earlier work on approximate range searching that I'll talk about later on. But there are many variants of the same idea. The fair split tree defined by Callahan and Kasaraju doesn't have logarithmic depth, and it turns out that property is not required for this. The logarithmic depth is used for other query problems, but I'm going to be using that in later talks. It turns out for just building well-separated pair decompositions, the BD tree that I described earlier, this tree is actually sufficient for well-separated pair decompositions, but for later applications, when I talk about various query problems, nearest neighbors and things like that, I'm going to be using this BBD tree. So remember this for next time. Not necessary for today, but for next time I'll be using this. So let me describe the construction that Callahan and Kasaraju gave. And this, like I said, is kind of... So as I mentioned before, the intuition behind the well-separated pairs is the notion that if I have a cluster of points here, and a cluster of points very far away, that I should be able to encode that cluster succinctly just using a single pair, rather than representing all the pairs between them. And if you're thinking in terms of, astronomy, where I have galaxies or solar systems, the separation distances are so large that you can understand that, having such a decomposition makes sense. The thing that is somewhat surprising is even if I give you uniformly distributed points, you can still form an efficient, well-separated pair decomposition for these things. So here's the idea. You begin by building a BBD tree, or excuse me, a BD tree for the point set. Okay, now in this case, I'm just going to do it in a simple manner. There are no shrinking nodes, but let's just imagine a standard quad tree. But if you had shrinking nodes, this would not be a difficulty. Okay. The way I'm going to represent a well-separated pair is by using a pair of nodes in the tree. So each well-separated pair is not going to be stored as a set. It's actually going to be just stored as a link, right? If I think of a quad tree as a set of nodes, what I will do to store a well-separated pair is basically this node will have a link to that node, this node will have a link to that other node. And in general, each node is going to have a series of links to all the other pairs that it might be involved in. These, I can think of the quad tree box as a representation, let's say, of the enclosing ball. That is, if I take the smallest enclosing ball, if those balls are well separated, then I'm going to consider these boxes to be well separated. And the construction works recursively as follows. So what I do is I start at the root. And at the root I have I start with actually a trivial pair. The trivial pair consists of the root node together with the root node itself. Okay? So now, if you think about this pair, it's kind of a weird pair because it's actually overlapping itself. But at this point, every pair in my set is going to be covered, right? Every pair can be represented as something in the root joined with something else that's in the root. Okay? But the root is, of course, not separated at all with itself. Not well separated, it's not separated, it overlaps completely. So what I do is then I break the root down into smaller and smaller cells. So let's pick it up at some point in the recursion. Let's suppose I have a pair of cells here. Generally speaking, I'm going to try to keep the quad tree cells of roughly equal size, usually either equal to one another or maybe one level apart from one another in terms of size. By the way, if you do a shrink operation, you may go to a cell that's very, very much smaller. If that happens, then what happens is the other guy is going to keep splitting until he catches up to this lower node. So I always try to keep the two cells as close as I can in size to one another. Okay? And then if I discover, I ask the question, are these two things well separated? If they are not well separated, then what I'm going to do is I'm going to then decompose them into smaller cells. Okay, and I'm going to compare them all. So this is one pair that I would consider, but I would also consider the other possible pairs as well. in my decomposition, right? So, in other words, whenever you break down from this level to the next level, I'm going to have to consider all the other pairs as well. Okay? When I finally get to the point that pairs that are well separated, then I stop the decomposition, and I'll just store this link in my data structure. And finally, observe that if you look at two leaves, you'll say, hey, wait a minute, those guys are never going to be well separated because they're touching one another. However, leaves, because the leaf contains only a single point, right? I can always think of two individual points as being well separated. I don't here look at the box. What I just do is I look at basically the point itself, right? A point is a kind of an infinitesimally small ball. So therefore, two such things are always well separated. So I'm going to decompose the internal nodes until they are well separated. And again, I always do this in a balanced, sort of a breadth-first manner, right? I keep decomposing and decomposing until I have cells of about the same size that are well separated. Okay? Either that or one or two things can happen. I can get to an empty leaf. If I get to an empty leaf, then I stop because there is no pair to be formed with an empty leaf. Okay? And if I get to two leaves that have points, then I stop there as well. Any questions about this construction, I guess? Because this is sort of fundamental to the idea behind the well-separated pairs. I'm going to talk about the running time, but I'm just kind of curious, do you understand sort of the recursion that's taking place here? Starting with pairs that are not well separated, decomposing until I get to pairs that are well separated, or until I get to pairs that are individual leaves. I think I actually put the code here, yes. Okay, so this actually is the construction. And I'm not going to expect you to sort of read this, while I'm running through it. But I want to emphasize the fact that the code itself is not a very complicated bit of code. It basically is just a simple breadth-first search. But during the breadth-first search, you are keeping track of two things. You're keeping track of, right, a node U and a node V, and the separation factor S, right? I check to see if these guys are leaves. If they're leaves and they're equal to one another, because I could have overlap, then I don't return any pair at all. If either node is empty, and by the way, I should talk about this concept of the representative. So I'm going to assume that in my tree, every node is going to store a representative point. So every node in the tree, right, represents all the points that are descended from it at the leaves. I'm going to bring up one of those points, an arbitrary point, and that's going to be the representative point. And this representative is going to be used in lots of my computation. So remember that every node in the tree has an associated representative. I'm also going to keep track of its level number in order to make sure that when I do the breadth-first search, I can do this in a balanced manner. Okay? If the two nodes are well separated, then I return that pair. What else? If the level of U is higher than the level of V, I'm going to swap U and V. Actually, I'm trying to think of what the level is. Yeah, the level is the depth. So the idea is I want to think of U as being the larger of the two children, or the larger of the two nodes. And then what I'm going to do is I'm going to break that node up into its children, and then I'm going to recursively invoke the well-separated pair decomposition using the children of U. Okay? So just a very simple breadth-first traversal of the tree. Well, not traversal, but a breadth-first recursion. Okay, and so let me give you the analysis as to why it is you get the number of pairs. So if you remember, what I was going to argue earlier was that the number of pairs you generate is going to be on the order of S to the D times N. And I want to explain kind of where this factor is coming from. This factor is coming from the fact, by the way, that this is going to correspond to the number of nodes in my BD tree. Okay? And what I want to claim is sort of where does this S to the D term come from? So to do that, I'm going to introduce something called a packing lemma. And this packing lemma, again, when I talk about approximation algorithms, will come up over and over again. So what does the packing lemma say? Well, the packing lemma says the following. Suppose I give you a ball of radius r, okay, in d-dimensional space. And what I'm interested in is the question of how many disjoint BD tree cells of side length at least x. Okay, so they could be of side length x like this node, or they could be of larger side length. But I'm interested in looking at just disjoint nodes. And I want to know how many guys could overlap this ball. Okay? And the claim is that the number of such nodes is going to grow essentially as, 1 plus, precisely 1 plus 2r divided by x raised to the power d. And I'm going to think of that as roughly r over x raised to the power d. I have to be a little careful here because it might be that r is smaller than x, and I don't want this number to fall to become smaller than smaller than 1, let's say. So it's generally speaking, it's going to be at least 2 to the d, because a ball, no matter how tiny, could always overlap 2 to the d nodes. But otherwise it's going to be defined by r over x, particularly if x is small relative to r. Yes. And so here's a simple sketch of the proof. So here's what we're going to do. Observe that I can take all of the quadtree cells and I can further decompose them until I get a complete grid. And by doing so, I'm only going to increase the number of cells that I'm looking at. So if I want to look at the worst case, well, let's just imagine everything has been decomposed down to this level x, right? Remember that I'm looking at cells whose size is at least x, so I never have to look at anything smaller than that. Okay. And then let's enclose this ball with a hypercube, right? Not necessarily one that's aligned with the quadtree, and then just ask, well, along any given dimension here, how many cells could overlap that guy? And it's actually easy to see that, right, since the side length of the box here is going to be 2 times r, right, the side length of these guys is going to be x, that the number of things that you could overlap is generally going to be 1 plus the ceiling of this term here. And since this is going to happen along each one of the d dimensions to get the total number of boxes, I just raise this to the power of d. Clear? Questions? Okay. So what this analysis showed is that the well-separated pair decomposition generates s to the d times n pairs. Oh, in fact, I didn't mention where the n is coming from. But remember, so what's the idea? Every node in the quadtree. Actually, do I explain this fact later on? Yes, let me actually go through the complete analysis. I'm sorry, I do explain this idea with the nodes here. So suppose I consider a given well-separated pair, u and v. Okay, to simplify the analysis, let's assume that they're of the same level. As I said, you're either going to be of the same level or at most 1 level difference. So that difference is only going to assert for a constant factor. Let's x be the side length of this pair. Okay, and here's what I want to assert. I would like to assert that, I know that if I have a pair that's involved with a well-separated pair, they're going to have to be at least a certain distance apart, right? If this is x, this is x. Well, these guys are going to have to be certainly, s times x, well, approximately, right? But the thing that I don't want to have happen is I don't want to have things that are extremely far apart be involved with one another. So I claim that not only is the distance greater than or equal to s times x, in fact, it's not much bigger than, let's say, O of s times x. Okay? And in fact, the threshold is this value, s plus 2 times x root d. But, well, this is kind of, let me see if I can go through the analysis here. So suppose not. Suppose that I had a pair of well-separated points that were much farther away than this. Let's say they were farther away than s plus 2 x root d. I want to argue that there's a contradiction, that this cannot happen. And what I do is I say, well, let's consider the parent cells. The parent cells would have size 2 times x. I'm ignoring shrinking here just to do the simple analysis. The analysis in general is made complicated by the shrinking process, but let me not worry about that. Just do the easy analysis here. So the parents are of size 2 times x. Okay. Notice if I enclose these balls, what can I say? Well, if this side length here is 2 times x, well, this side length is x. This radius here is going to be x times the square root of d, right? So x root d is going to be the length of this quantity here, okay? And therefore, if I look at the what do I want to say here? If I now look at the separation, given what I had before, right? The assumption was that that these two guys were separated by distance s plus 2 times x. So I have s times x root d plus 2 times x root d. I've gotten rid of an x root d from this distance here and x root d from that distance, so that gets rid of the 2. So what I have left over is s times x root d. But now I have a ball of radius r, x root d, right? And I have a separation of s times x root d, so s times r. So the parents were already well separated. So the point was the algorithm would have never gone down to the children, right? The recursion would have stopped at this level here. So in summary, what happens is I can assume that essentially all the well-separated pairs that I report at the end of the day have the property that if x is the side length, they're going to be separated by a distance of at most s. And now I go back to my packing lemma. Okay? If I ask this guy, well, how many boxes can be within this distance, okay, and are of about the same size, By the packing lemma, what I get is it's going to be this quantity here divided by essentially x. And so the x is going to fall out. I'm going to get s plus 2 root d raised to the power d. I assume throughout that d is a constant. Okay? So essentially all of this stuff falls out, and then it's just s to the d is what's left over. So the total number of pairs for any given node in the tree is going to be s to the d times n. And then I just add this up over all the nodes in my tree. Okay. So, well, let me first, before I go on and start talking about applications, let me just ask if there are any questions about the analysis here. Okay. This style of kind of a packing argument analysis gets used a lot in approximation algorithms. And in later talks, I'm going to be making reference to sort of packing arguments. Packing arguments generally are used to bound. If I have a large, let's say, set of boxes, a grid or something like this, that overlap a constrained region of space, this packing argument is what is used to control the complexity of these things. Okay, so I'm going to give you 3 applications of well-separated pair decompositions in approximation algorithms. And they're actually, well, if you look, I looked in the Wikipedia entry on well-separated pair decompositions, and I think there are 5 applications that are listed there. Okay, so these are kind of the canonical examples that everyone gives as to, you know, how it is you use well-separated pair decomposition. So after this lecture, you will know 60% of the canonical examples for well-separated pair decompositions. And I apologize for those of you who've seen this before, but maybe good to review these things. Okay, so what's one standard example is the closest pair algorithm. So I give you a set of points, and what I want to do is I want to find the pair of points that are closest to one another in this set. Okay, so how do I do that using a well-separated pair decomposition? Well, again, I don't want to look at all pairs of points. And by the way, if you take any algorithms course, you will learn about a simple divide and conquer algorithm for computing closest pairs using, you know, this technique you may remember. You divide the points in half and you look at this central strip. That algorithm, well, works well in 2-dimensional space, right? But it uses the fact that you reduce this to a 1-dimensional search problem. The nice thing about the well-separated pair decomposition is it works in any dimension. So what I do is I compute a well-separated pair decomposition. The separation factor that I use is going to be 2. Actually, I'm sorry, I have to use a separation factor that's just anything bigger than 2. So pick a number that's just slightly bigger than 2, and then build the well-separated pair decomposition using that value. I'm going to associate every well-separated pair with a set of representative points. So let me just, I guess I'm going to illustrate this, but throughout I'm going to always assume that whenever I give you any set of well-separated pairs, okay, so this is going to be U, and this is going to be represented by node V. There's always going to be a point P of U and a point P of V that represents these guys. This is the lowercase. The set capital P of V denotes the entire set. I'm sorry, P of U and P of V denotes the entire set, and the lowercase p and the lowercase p denotes the representative point. So I'm going to assume there's a representative point here. And what I'm going to do is I'm just going to look at all these representative pairs over all the points, and I'm going to return the one that achieves the minimum distance. So I use the double bars here for Euclidean distance for these guys. Okay? And obviously the running time is just going to be the running time of the well-separated pair decomposition. So this is the amount of time it takes me to build a well-separated pair. S is basically 2, so this is 2 to the d. So that's for me just going to be a constant factor. So the running time is n log n. Okay? And then let's look at the correctness argument. So suppose that x, the pair xy is the true closest pair of my set. And suppose that this pair has not been output by the algorithm. So I want to kind of come up with a contradiction argument as to why the algorithm is correct. So suppose it was an output. Well, I know that there must be some well-separated pair that encloses x and y. Okay, so let's take a look at that well-separated pair. Now, P and U and P of V are the representatives, and these guys were actually going to be considered as a candidate for the set. One thing I can say for sure is this. Because xy was not output, right, I know that either x is not P of U or y is not P of V. It might be that P of U is equal to x. It might be that P of V is equal to y, but both of those are not the case, because this was one of the pairs that was considered by my algorithm up here. And if xy are the true closest pair, then I would have output that pair. Okay? So the reason I failed is because I essentially output a pair that's not there. The other thing I know as well is these guys can be enclosed in balls of radius r that are separated by a distance that is actually, I wrote greater than or equal to 2r. Well, in fact, it should be bigger than that because it's going to be strictly greater than 2r because my separation factor is strictly greater than 2 here. So this greater than or equal sign should actually be a greater than sign. Okay? And from this I can conclude the following. So therefore, if I look at the distance between x and p sub u, right, I know that one of these pairs is distinct, right? These are in a ball of radius r, therefore the distance between them is at most 2 times r, but these guys are separated by a distance strictly bigger than r. So that means that these pair of points are closer than this pair of points, but I began by assuming that xy was the closest pair of points, so I get a contradiction from that. Okay, so therefore, the closest pair will actually be, they'll effectively be singletons inside of some well-separated pair. And the number 2, of course, is important because this is exactly what you need to get this property to hold. Next time I'm going to talk about Euclidean minimum spanning trees, and we're going to actually see the same well-separated pair decomposition with a separation factor of 2 coming up again. Questions about this? For 2 sets to be well separated, they can be enclosed in balls of radius r. So if I just look at the smallest ball that encloses the quad tree box, if this has radius r, if that has radius r, then by the condition of well separated, these will be separated by a distance of s times r. S was chosen to be greater than 2, so this will be greater than 2r. Okay? Now the other question was, how can I conclude that these points are not the same? So here's what I want you to imagine. Suppose that x was the representative point, and y was the representative point over here. Remember that my algorithm works by looking at all the pairs pu and pv of the representatives, and it gives me the shortest such pair. X and y, I chose x and y to be the closest pair, so there can be no pair closer than this. So if x was pu and y was pv, when I returned the minimum of these guys, I would have returned xy. Okay? But the hypothesis here was I did not output xy. In other words, I made a mistake in the output. So therefore, I can conclude that one of these two things must be true. X and y cannot both be the same as the representatives. Okay? So since one of the points cannot be the representative, take the one that is not the representative and look at that pair of points. And the claim is these guys are closer together than these guys. But then again, my hypothesis was that xy was the closest pair. So that's a contradiction. Okay? Okay. How are we doing? We got a little bit of time. So next, let me go to the opposite extreme. The opposite extreme is computing the farthest pair of points. Now, the interesting thing here is I'm not going to be able to get an exact algorithm. So in the closest pair, I was actually able to show that I could get exactly the closest pair. Here, I'm going to approximate the diameter. So let's let P be an n-element point set. The diameter is defined to be the pair of points that are farthest apart. Okay, or I can think of actually diameter as just the distance between these points. I'm going to be kind of ambiguous as to whether it's the pair or whether it's the distance. Okay. And my objective is this. I would like to output a pair of points x prime, y prime that are not necessarily the diameter, but let's say they should be close to the diameter in the following sense. That if I look at the distance between x prime and y prime, right, it cannot be any bigger than the diameter because the diameter is the farthest pair, but it should not be much smaller than the diameter either, okay? So let's say diameter divided by 1 plus epsilon. So again, as you make epsilon small, right, x prime, y prime should be arbitrarily close to the actual diametrical pair. And again, these points will be chosen from within my point set. So I want to see about how I can use well-separated pairs to solve this problem. So this is a very common application of approximation algorithms using well-separated pairs. Step 1, I compute an S well-separated pair for an appropriate value of S. Okay, now what is appropriate? Well, 4 over epsilon turns out to be appropriate here. And you might say, how did you know that 4 over epsilon was the right value to use? The answer is because I looked forward and I looked at the next slide. In the next slide, when I do the analysis, it shows me that 4 over epsilon is actually the right value, and so I plugged it back in. But usually when you do these things, you just start by assuming you have some value of s. Usually it's going to be a function of 1 over epsilon, and then you kind of engineer the constants after you're done. So how do we do this? Again, remember that every well-separated pair is going to be associated with representative points, right? So for every pair, I just have 2 arbitrary points. Yes. And then what am I going to do? I'm going to return the maximum over all of these representative points, over all the well-separated pairs in my set. So just exactly the same as before, but before I did this for the minimum, now I'm going to do this for the maximum of all these pairs. Okay? So for example, for every one of these pairs, I'm going to look at the representative pair, and I'm going to choose the points that result from that. Okay. The claim is going to be that the running time, I'll talk about correctness later, but the running time will be just the amount of time it takes to build a well-separated pair. That's n log n plus the size. By the way, remember the n log n came from the time to build the quad tree. This was the time to actually generate the well-separated pairs. So since s is essentially O of 1 over epsilon, this is going to give me n divided by epsilon to the d. Typically in applications where epsilon is going to be a small number, and the dimension is, let's say, non-trivial, usually this term is going to be larger than the n log n term. Okay, and so let me argue that this is going to be a correct approximation. So let's start by beginning with the diametrical pair xy. Okay, let's let u and v be the associated well-separated pair, right? Every pair will be separated. Let's let pu and pv be the representatives for that pair. Okay, let's let r be the radius of the enclosing ball. So what do I know? I know that, well, everything within here is going to be within diameter 2 times r. So x and pu are going to be within distance 2r. Y and pv will be within distance 2r. Okay, and so therefore I can conclude that the distance between x and y, right, is going to be at most the distance between p and u and the distance from x to pu and the distance from pv to y. So this is just triangle inequality. So therefore, the distance between x and y is going to be at most the distance between pu and pv plus 4 times r. Okay? By the separation properties, I know that these two balls are separated by distance s times r. So therefore, pu and pv are separated by distance at least s times r. Or in other words, r is less than or equal to pu pv divided by s. Okay, and then if I combine these two inequalities, what do I get? I get xy less than or equal to pu pv plus 4r. Okay, but remember, r is less than or equal to pu pv divided by s. So this 4r becomes 4 over s times pu pv. Combining this, I get 1 plus 4 over s times pu pv. And that's going to be equal to, well, because of my choice of s is 4 over epsilon, right, yes, this is going to give me 1 plus epsilon times pu pv. So in other words, it's going to follow that basically my pair pu pv is going to be epsilon close as a representative to the actual distance between the diametrical pair. So therefore, pu pv is an epsilon approximation to the diameter of p. Okay? Okay, kind of like the previous analysis, right? Build a well-separated pair. Look not at the actual points within the set, but just look at the representative points within that set, and kind of make use of the fact that, the distances here are so small relative to the distances in between that, approximately speaking, the distance between the representatives can be used as a representation of the distance between the original points. Okay? Questions about this? How are we doing on time? I still have a few more seconds left. Let me mention, by the way, that look at this number 1 plus 4 over s. Okay? This number is actually going to reappear a couple slides from now. And this quantity 1 plus 4 over s is actually this number occurs, actually there are 2 numbers that occur all the time in analysis of these things. Yes. The 1 plus 4 over s occurs at one end, and there's another one which is essentially there's an r over s that occurs as well. But let me get to my next example. Okay, so the last example I want to give is the example of what is called Euclidean spanners, spanner graphs. So what are spanner graphs? We're given a point set P. The Euclidean graph is defined to be just the graph, the complete graph on all these points, where the weight of the edge is just the distance between the points. Okay? The problem with the Euclidean graph is, right, its size is quadratic in n, and this is not a good thing. So what is a spanner? Well, if I give you an approximation factor called the stretch factor t, a t-spanner is a graph on the point set such that the path in G between any 2 points is roughly the same as the Euclidean distance. So in this example, let's say if I pick 2 points like this point and this point, there is an edge between them of a certain length, right? And there's also a path in the graph G. And I would like the graph G to have sort of enough edges that the length of this path here should be about the same as the length of the Euclidean edge, right? So you can think of a t-spanner as sort of a road network, right? A road network that has the property that if I drive along this road from any point to any other point, I'm not going to be going very much farther than if I got in my airplane and flew from one point to the other point. Okay? In other words, the distance between the points in the graph is at most t times the actual distance between them. A little bit of notation. So when I talk about distances in G, I'm going to be using this term xy. This is my Euclidean distance. And I'm going to be using this xy sub g. This is essentially the path length in the graph G itself. Okay? So let's look at the construction. So the spanner construction works as follows. So we start with the point set and we start with the value t. As always, I begin by computing a well-separated pair for an appropriate value of s. Okay? Again, what is appropriate? Well, isn't it completely obvious that this is the appropriate value? Again, I have no clue as to why this is the appropriate value, but I just go through the whole analysis, and at the end of the day, I figured out, well, what value of s is going to make the inequality work, and I plug that value in. Okay? Remember, t is a value, t is the stretch value, so it's going to be a value that's bigger than 1. So notice t minus 1, as the stretch factor gets closer and closer to 1, right, that would be a perfect spanner when t actually hits 1. And as you would expect, the denominator here, if t actually hits 1, is going to go to infinity. So the idea is you can get closer and closer to 1, but of course you're not going to be able to exactly get the value of 1. Otherwise, you'll just go right back to the complete, Euclidean graph. Okay. We're going to associate, again, every well-separated pair with a pair of points. So if this is a well-separated pair, P and U, there's going to be a set of representative points, PU and PV. Okay? And then here's what I'm going to do, going back. If I have some well-separated pairs go directly between the points. Remember, if I have a leaf-leaf well-separated pair, I just join those 2 points together. But other well-separated pairs go between an internal node and an internal node of the quadtree. So there's many points being connected. Okay, so here, perhaps there's 1 point, but over here there's multiple points. What I'm going to do is very simple. I just have to make a connection between them. I'm going to join the representative points together and create a new edge in my graph. Okay? And I'm going to start doing this for other pairs. So if I've got another pair over here, right, I'm going to pick their representative pairs and add an edge there. Another pair here, pick the representative pairs, add an edge. Okay? And I just keep continuing this process, right, until finally I've considered all the well-separated pairs and I wind up with this graph. Okay, I want to claim that if you have chosen S to be this value, that the result that I get will be a t-spanner. Okay. Well, what is the running time of the algorithm? The running time is just going to be proportional to the time to build the well-separated pair decomposition. Since S is this term over here, the t factor, right, I want to think of t as being a vector that's going to be small, close to 1. So typically, I'm going to think of this as just being a constant. The term that's going to dominate is this t minus 1 to the power d. Okay? Okay. So to prove the analysis here, to establish the analysis, what I'm going to do is I'm going to give you this little utility lemma. And as promised, this quantity 1 plus 4 over s shows up in the analysis here. So the utility lemma says the following. Take any well-separated pair. Take 2 points x, x prime that are in one of the heads of the well-separated pair and y prime that are in one of the other heads of the well-separated pair. Okay? Then the distance I want to do is I want to compare the distances relative to the distance xy going between the two. 2 points in the same head are going to be close in the sense that their distance is going to be 2 over s, right, times the distance. And it's easy to see why, right? These guys are within distance 2 times r because r is the radius, 2r is the diameter, so therefore the ratio between this distance to this distance is going to be essentially what? 2 divided by the separation distance of s. Okay? And the other thing is if I take any 2 points in different heads, their distance is going to be relatively close to x and y. Okay? That is 1 plus, remember, think of s as a big number, so this number is generally going to be fairly small. It's going to be approximately equal to x times y, or x, I'm sorry, the distance from x and y. And why is this? Well, again, think about it. These 2 points are within distance 2r. These are within distance 2r. These are within distance sr. The same inequality that I used before that gave me the 1 plus 4 over s can be applied here to give me the same value. Okay? I guess in the worst case, I could consider a situation where if x and y are as close as they could possibly be, they're exactly at distance s times r. If I put x prime and y prime as far as they could be, okay, they'll be at sr plus an additional 2r plus 2r, so sr plus 4r, okay, 1 plus 4 times s, and then when I compute the ratios, I get this value here. Okay, so here's the final analysis of why I get the stretch factor. So pick any pair that you want. Okay? Let's let x, y, g denote the distance in the graph, g that I've just constructed. Let's let pu and pv be the representatives for these guys. Okay, and I'm going to apply sort of an inductive argument here. How does the inductive argument work? Well, okay, so what is the distance between x and y in my graph g? Okay, so what's going to happen is this. There's going to be some path from x to pu in the graph, and I'm going to apply induction because the distance between x and pu is smaller than the distance between x and y. Right? There's sort of an idea that this distance is at a large scale, whereas this distance is occurring at a much smaller scale. So I'm going to imply the induction hypothesis here. There will be some path in here. What I can assume about that path is the distance between x and pu in the graph is going to be at most t times the Euclidean distance between these guys. Once I get from x to pu, right, remember in my construction, I connect these 2 points by an edge in my graph. So the next step will be of length pu, pv. Okay, and then once I get to pv, then I'm going to follow that path to y. And again, by applying the induction hypothesis, the distance between these two guys and y is going to be at most t times the distance between the 2 points. Okay, so by the triangle inequality, I can argue that the distance between x and y and g will be at most this. By the way, you might say, well, how do you know this is the shortest path? I don't know that this is the shortest path, but I know that there exists a path of this length. So therefore, the shortest path cannot be any longer than this. Okay, so there will exist a path of this length. And then let's do some simplification here. So x, pu, these are 2 points within the same head. Okay, by the analysis, this is following from the first rule up above here. When I have 2 points in the same head, their distance is at most 2 over s times the distance between the pair of points in different heads. So this is 2 over s from the lemma, and the t comes down here. Pu, pv, well, again, this is going to follow by the second rule here. Think of this as pu, pv over here, xy over here. I get 1 plus 4 over s multiplied by the distance between the points. And then t times pv and y, this is exactly symmetrical to the x pu. This is just going to be t over s. So when I put these guys together, what do I get? Well, let's just see what I get here. I mentioned to you that there was some sort of, so I get 2t divided by s plus 1 plus 4 over s, 2t divided by s. Yes, so this is the term I've got. Putting this together, what do I get? I get 4t over s combining these terms plus 1 plus 4 over s. I guess I can combine these s terms, so I get 1 plus, let's see, what is this? 4 over s times t plus 1 Okay, and if you remember, what did I set S to? S was I set equal to something like, it was t plus 1 over t minus 1. Let me just go back and recall. Well, actually, I should just be able to, 4 times t plus 1 over t minus 1. But I guess actually I can see from this point how it is I want to derive it. Because really what I want to get at the end of the day is I want this number here to be less than or equal to t, right? So if I plug this value in, right, what do I get? 1 plus 4 t plus 1 divided by s. So this is 4 times t plus 1 divided by t minus 1, right? These cancel, the t minus 1 goes up on top, so this becomes, right, 1 plus t minus 1, and so that's going to be equal to t itself. So in other words, I've just sort of engineered the value of s to give me exactly what I need for it to get the final spanner value, the spanner stretch factor that I want. Okay. Questions about this? Okay, I see that we are out of time here. So let me conclude, I guess, by observing, what? So the well-separated pair decomposition is this very nice thing. It provides us with a way of taking this n-squared collection of pairs and representing them succinctly using a number of pairs which is going to be more like linear in n, along with a separation factor, right, depending on what that term is going to be. The construction is quite simple, right? This is very practical, very easy to implement, unlike a lot of computational geometry, which becomes hard in d-dimensional space. At least the implementation is fairly easy. Of course, there are going to be, big factors that depend upon d. So you can do this in dimension, I don't know, 1 through 10 perhaps, but I don't think I would apply this to much higher dimensions than that. We gave 3 examples here of problems for which this could be used: closest pair, approximate diameter, t-spanner. There actually are many, many more problems that can be used here. All nearest neighbors, for every point I want to compute its nearest neighbor. Next time I'm going to talk about how to use this for the Euclidean minimum spanning tree. The kth closest pair, so we did the closest pair, we did the farthest pair, the diameter. In fact, you can generally compute the kth closest pair efficiently using this algorithm. And I think that's all I had to say. Yes, so thank you very much. And let me answer any questions that you might have. Yes?
About that donut cells and
yes.
how they split and what are the leaves and both?
Yes, good question. So for the donut cells, I didn't spend a lot of time discussing that, but this is a useful thing because I will need to use this concept later on. So the decomposition step looks something like this. Okay, let me get the better marker over here. I think the decomposition looks something like this. There are actually 2 different versions, right? There was the simple splitting where I just had a whole bunch of points in some very tiny region here. So here I just computed the smallest quadtree box that I could compute. Okay, so starting if this cell here was associated with some node u in my tree, when I detect that the points, let's say the smallest bounding box is much, much smaller, then what I do is I store in here a representation of this box is actually stored inside of the node internally. Okay, and then what happens is this subtree here is going to represent these points. This subtree here represents this entire sort of donut region, okay, on the outside here. So it's going to be a leaf node, okay. This is going to be a leaf node, and what I store in the leaf node is going to be the outer box and the inner box. And like I said, it represents this sort of region of space here. It represents on the stuff on the outside, but not the stuff on the inside. Why? Well, because the stuff on the inside, this guy is stored in this tree here. The other one I talked about was the centroid shrink. Okay, and this happens when you have clustering. If I have, let's say, a dense cluster of points in here, and maybe a sort of a loose clustering out here, then what I do is I shrink down to a box that contains a constant fraction of the points. Okay, and the same structure shows up. So if this is u here, right, there's going to be a node for u. I store this box on the inside. So let's say I'm going to think of, there's maybe, P prime being the points in here, and let's say P double prime being the points out here. And then what I'll do is, in this subtree, I'm going to recursively compute a quad tree or a BBD tree for the points at P prime. And for this guy out here, I'm going to compute the points for the guys that lie outside of this region here. Does this answer the question, or? The next level of the tree. Okay. And which one do you want to split? The outer one or the inner one? Okay, the outer one. Okay. Actually, now you're asking me a good question. Because one of the issues here is that I would like to maintain the property that each node has at most one sort of internal box inside of it. So let's suppose I go to then split this guy. And let's imagine that I have a similar distribution that is relatively clustered, okay? So let's suppose, again, there's some loose agglomeration of points here. We've gotten rid of these points here, right? They're part of the other tree. Okay, so P prime is stored in here. And then let's look at what's going on out here. Suppose there's a loose collection of points, and then in here I've got, and let me do this maybe in a more representative manner, okay? Let's say in here somewhere there's a very dense cluster, okay? Now, there's a danger here, which is the next step that I would like to take is I would like to then shrink in on this set of points, okay? And then, so let me call this point, these would be P double prime, maybe P triple prime, and these points out here would be P to the fourth or something. But I don't actually want to do this, and I'll tell you why I don't like this. Because if I do another shrink, now what happens is these points out here, P to the fourth, right? 1, 2, 3, 4, okay? The problem is that this cell actually has two holes. And we all know, anybody who knows anything about a donut, right? A donut can only have one hole, not two holes. So we actually do this in a series of operations. We actually first shrink down to this point. We then split this guy in half. And then we shrink to this point. Okay? So the shrinking operation is a bit more complicated. And this is just done to guarantee the fact that every cell will have within it a single hole. So the way in which this would actually be done is I would actually, here, I would do a shrink operation, okay? In one of these children, I would do a split operation, and then within the corresponding child here, I would then have another shrink operation that would take place. So this centroid shrinking is a little bit more complicated because I want to maintain this property that every one of these cells has at most one hole inside of it. Okay? I don't want to eat up the entire coffee break here. Any other maybe quick question that I can answer? Okay, if not, then let's break for coffee and yes. Thank you very much.